Hello, everyone. Thanks for coming. My name is Cesar Sewell. I am a Research Computing Associate for the Center for Advanced Research Computing. And today I'd like to talk about software management. And software management can mean a few different things. But for this context, we're going to talk about two main areas. First is we'll talk about the software that is installed and available on our system and how it's presented through the module system. And then the second part will be what happens if you want to install your own software because it's not available on the software stack that we provided. So as you may have encountered, software can be really complicated, and not just using it, but just getting it running. So for example, we have this package. I'm just going to pronounce it as Aries, and it relies on other pieces of software for functionality. And in turn, some of those pieces of software rely on other software, and you do that a couple times, and eventually you get a very complicated dependency web as shown here. And every one of these things must be working, and they must be compatible with each other in order for Aries to work properly. And that can be a really daunting thing to have to install everything by yourself. So we try and take care of that for our users. And one way we do that is by using this utility called SPAC. And it allows us to leverage the community. Basically, everyone or some people take an application that they like, they put in build instructions and they put it into SPAC. And then people take those build instructions and then they build other things. And before you know it, you've got a ton of different applications, and you don't have to be an expert in everything. And you can have a pretty extensive tree of software. And that's what we've done. And if we wanted to leave it there, you could just go to this path here, SPAC apps, Linux CentOS, x86, should be 64. But it says 84. I'll fix that typo. Actually, let me just fix that right now. Okay, there we go. Looks better already. So yeah, if you wanted to, you could just go to that directory and start using the applications. But that would be kind of madness because you'd have to track down every dependency possibly. So instead, what we do is we use another tool called Lmod, and that presents software to you, and it does a couple other things, such as it sets environment variables for you to actually use the software. You can search through using Lmod to find what is available. It'll give you some documentation on how the package was built. It's not exactly in plain English. You kind of have to sift through it, but it's in there. Tells you where the package is saved to on the file system. And it tries to prevent you from loading incompatible software. I don't think we've had a problem, but I'm always a little bit like wary to say like you'll be 100% safe no matter what. But the idea is that it makes it hard for you to load software that doesn't work well together. By default, when you log in, you get a USC module. And that contains a GCC math library known as OpenBLAS, an MPI library, and then this PMix package that OpenMPI needs to run. And we can look at module avail, and I'll do this in a minute. You can see what's available. And then depending on what modules you have available, it'll show you new modules. So some stuff will appear hidden, and then when you unload stuff that's compatible with that will be shown. And basically, there's 4 kinds. There's a compiler, there's a BLAS, which is a math library, there's MPI, which is a parallel computing library, and then everything else. Oops. So let me, where's my terminal? There we go. Let me just share my terminal. I think this makes it a little bit easier. So I'll run this module list command. I have no modules loaded because I was messing around with my modules earlier. So let me just reload the USC module. So module list. So here I am with the default module set. And if I wanted to see what modules are available or what software is installed, I could type module avail. And it returns a bunch of stuff. And I don't know if you can see how well you can see this, but it's kind of grouped up into different blocks. And these represents the 4 different categories of modules. So let's see, I can scroll. So the biggest category is this one right here. This is everything compiled with just the GCC compiler. And then you have this smaller category, everything compiled with GCC 8 and OpenBLAS 038. We scroll up a little bit. Everything compiled with GCC 8 and OpenMPI 402. And then this is GCC 8, OpenBLAS 038, and OpenMPI 402. So if you wanted to use a different version of OpenMPI or a different version of OpenBLAS, or you didn't want to use OpenBLAS, use a different BLAS library, you would see different stuff. Let's go back to the slides. Where's my slides? Okay, so this is just what I showed you. Because we'll just call it a safety feature. Because of the safety feature where it tries to hide stuff from you if you don't have the prerequisites available, sometimes you can type module avail, and it looks like the software is not there. If that's the case, you can use this utility module spider, and it'll search the whole tree, and it'll look for that software. I'll go back to my terminal, and I'll show you what I mean by that. If I do module purge, module list, so I have no modules, module avail. So I have some stuff. Looks like I have my own module tree. Let's ignore this for a minute. But it's definitely less stuff than what we were seeing before. In fact, all I was seeing is like these core modules. And let's say I wanted to know about R, so I do module avail R. And it says there's no R available. But we know it's there. So if I type module spider R, I get a bunch of results. So first you get versions, and then a list of different R versions. And then underneath is a bunch of stuff that has the letter R in it. So if you don't remember the name of the package, or maybe part of the name, this would be helpful. But R is kind of an unfortunate name because the letter R is in a lot of unrelated package names. But let's say I wanted to load R, let's say 363 module spider, and then R363. And module spider reports that I must have these two modules loaded before I can see R. So I'll type module GCC 0.3.8. Module avail. And then here's all the different R versions. So now I could do module avail R. I can see there's R, and then same thing, the same problem we had earlier where everything that has just the letter R in it. Let's go back to those slides. Oh yeah, so there's another feature, which is, let's pretend, we had all of these modules loaded here. You can switch modules, and as a result, it'll reload different stuff. So if you were to run this command with all these different modules loaded, let's say we wanted to switch from the GCC compiler to this Intel 1904, a bunch of things will happen. So some modules will go inactive. Some modules will get reloaded to the versions compiled with this compiler. And then some, just because the way that we manage our software tree, they might be reloaded, but with slightly different versions. So this, again, it's to make sure that you're not mixing compilers, because that could cause problems when you're using applications. You may not interact with each other well. Like I demonstrated earlier, you can use the module avail command to see what's available. You can use module load. Let me just do this demo. So I could do something like this, which Python. The operating system comes with a version of Python. Module avail Python. And there's a couple different versions of Python. I have some that I was playing with, and these are ones that you'll see in the GCC 8, compiled by GCC 8. So I do module load Python 3.7.6. 3 Python. So now I'm using one that's been compiled. I can do like Python. Talked about that unlocking feature. And this is a kind of interesting feature. If you find that you have to load a set of modules frequently, you can use the save and restore functionality, and you give it a name, and you can have basically your own environment. And I can show that real quick. So I could do a, oops, module saved list. Module saved list. So I have a CUDA, something called numerical, something called rely on. Module describe. I was trying to build the software, and it needs a whole bunch of modules, and so it would be kind of a pain to manually load all of these, or I guess I could create a script. But this is a nice feature because you could load in an extra module and type module save, and then I'll add it. Okay, just switching back and forth. If you wanted to create your own module files for software that you have installed yourself, you could do that. I don't know how much detail I want to go into this, but you would have to create your own tree similar to this. So you'd have to designate some directory where you're going to save all of your module files. And then underneath there, you would have different directories of the software. And then underneath that, you would just have files, which are what we call the module files. And these are like scripts that describe what the module does when you load it. And then after that, you would run this module use command. And then you could run this module avail. Here's an example of what a module file would look like. Usually there's like descriptive help functionality, but basically, I guess the most important parts is there's setting environment variables, your prepending path, if it relies on other modules. You could put in load commands. So we have a question, how to save module list. Can I demonstrate once more? Sure. Okay. Module purge. Let's say module load GCC, module load MATLAB, module load Python. So let's say I use these. I have some kind of a workflow that uses these three. So I could say something like module save, then I'll just say workshop 226. So save current collection of modules, and that gives the name of the module save list. So I have a new module collection here. Module purge. I have no modules, and I could do module restore workshop 226 module list. So I have all of those. And then if I wanted to load one more, like module load module available. I'm just going to pick this random one, Mother, module load Mother. Not sure what that is, but I could do another module save workshop 226. So I could just append. We have another interesting question. If you download a Perl script that starts with user bin Perl, and then you load a Perl version, you type which Perl, you get a crazy Perl, crazy long name Perl. You need to change the Perl invocation in the downloaded script. Yeah, usually what I've seen is instead of like user bin, I've seen user bin, I think it's env Perl. There's I forget what it is. I'll have to look up the syntax. But basically it's this command, which I cannot remember. I see it all the time. It's a command that basically gives you the path to the Perl. So if you do a which Perl, it'll report this crazy one. It's driving me crazy. I don't remember what it is. It's like one of those things on the tip of my tongue. I'll look it up and I'll get back to you on that. But yeah, you'll have to change your script, at least just that little shebang part. Okay, I'm gonna go back to the slides. Oh yeah, so I was talking about how to write your own module file. Yeah, so you would include like set environment, set path. compiler load dependencies. Here's an example from Python. If you wanted to have your own Python module, you could take an example like this. And so here's just an example of what you would have to change. And then if you want to go into more detail, there's a Discord page on our discourse page. And you can click on this link, or you can go to our HPC-discourse, and you'll find it there. And it goes into more step-by-step details. Okay, now we're going to go into the installing software portion. So there's, I guess, different levels of difficulty when you're installing software. Probably the best case scenario is what's known as the precompiled binary. And basically, someone who develops software, if they're kind and good at planning, I guess, they'll compile the software and make it available to you for your specific operating system. I guess this happens a lot, like on the Mac. If you download like FileZilla or something, they just give it to you and you download it, you open it, and you run it. But for one reason or another, you may have to compile it yourself. And if the developers make their software available, often they will include some kind of a build system with it. So it makes it easier for you to compile it. And that can be hard to do, or depending on the build system that they choose. And in a worst case scenario, you may be in a situation where you have to use old dependencies that are no longer maintained for this reason or that reason, which sounds bad, but it happens more often than you'd think, I guess. So yeah, sometimes it can be easy, sometimes it can be really bad. But in any case, one thing to keep in mind is where you install the software. In an environment like your laptop, where you own the computer, basically you're the system administrator. Which I don't know if you've ever seen those errors pop up, like you have a problem on your Windows computer and it says contact your system administrator, and that doesn't really mean anything because you have to call your own self for help. But on a system like HPC, we have system administrators, so yeah, you can talk to us and we'll help you. But the trade-off is that you don't get to manage the system. We manage the system, so we are in charge of what software gets saved and where it gets saved to. You may also have noticed when you install software, a little pop-up will show up and it says, do you want to install this for everyone on this computer, or do you want to install it for just this user? So it's kind of asking you, do you want to do a global installation or do you want to do a local installation? And typically when you do a global installation, it gets saved to a path like user bin or user local if you're on a Linux computer. And if you want to save here, because it's a global installation, you must have root privileges. And that's a security thing because, and I guess also just a politeness thing, because if someone is running a piece of software, you don't want some rando changing that based on their own whims while you're using it. So we require root privileges. So you may see online, oh, it's so easy to install the software. Just type yum install blah, 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 or apt after this or apt that. That is a system administrator type command. So that's not available. So you'll have to do a local installation. So local, what does that mean? Well, it basically means a place that you have write privileges. So typically that's your project directory, so project ID, and then your username. And then once it gets saved there, you only need to install it once. And then no matter where you are on the cluster, it's accessible. So no matter what compute node you're on. If you're on the login node, you can see it. If you're on a compute node, you can see it. If we buy new compute nodes, you can still see it. But you'll have to read the documentation for how to do a local install. And it's not always documentation quality varies. Okay, so before we get into like actually installing software, let's do a quick tangent sort of on environment variables. So we saw earlier that module files, they modify your environment variables. And what do environment variables do? Well, basically they're variables and they are like string values and they set behavior or they're just convenient things. So if you want to have like a variable called my data, you could just type cd to my data and it goes here. Or there's other variables that like look for, let's say, where your home directory is, so it can save something easily. And by convention, if it's set by the system, it's uppercase. And if the user is doing something, it's my data, lowercase, just like this my data variable. But it's not necessarily, it's just a convention. And then to use it, you put like a little $sign in front. If you want to see every environment variable, you can do this env command. So let me just do this on the terminal. Oh, happens every time. Okay. So important environment variable is the path environment variable. So here I am with the pretty, since I don't have any modules loaded. This is a list of directories separated by a colon. Here's one directory, then a colon. Here's another directory and a colon. And basically, anytime you type a command like this, which I will not attempt to pronounce, what happens is the shell looks in every one of these directories for something with this name. And if it doesn't find anything there, then you get this command not found message. I could type, for example, Python. And Python starts up. I do which Python. It's saying Python lives in user bin, and user bin is in the path. I type Python 3.7. There's no command not found. If I do module load, GCC, and then Python 6. Do which Python 7, so it can find. So modules modify environment variables, and environment variables determine behavior that you're gonna, I guess, experience on the cluster. So here's this crazy path. When the modules add stuff to the path, you get these crazy, crazy long paths. It's like Luigi didn't even want to type out an example. He just put a bunch of dots. So that's kind of annoying that you have these long paths, but we'll get to that in a minute. You don't necessarily need to know this huge chain because the environment variables take care of that for you. So here's a really simple example of a precompiled binary. Maybe you've seen this. You go to your project directory. It'll say download this file, like a tar.gz file or a .zip file. Then you extract the file. Maybe you add the file to your path, or maybe you even read directions and it says add to your path, and maybe you didn't know what that meant. It means add the directory, usually a bin directory, to your path environment variable, and you're prepending it. That's what this colon $sign syntax is all about. And then you can just run it. So this is like the easiest, I guess, best case scenario. You just download and extract. But it's not always the case. Oftentimes you'll have to compile software. So for example, the process of compiling software is you get source code, which is like a .c files or Fortran source code files or header files. That goes into a compiler and the preprocessor, and that gives you something called an object file. And if your software relies on other programs for functionality, the linker comes along and it looks for those library files. So you can shared object file or this archive file, and it links them, and then it creates something referred to as the binary or an executable. So this is the thing that you run. So here's an example of if you had a program that was just like a C program that was just one file, you might run a command like this. So GCC, and if there's any GCC flags, like you want to get all warnings enabled, and you want to do this level 3 optimization. You want to do any of these CPP flags or LD flags, basically where are the libraries installed, and then you can create a my program binary. So that's if you have one, your program just exists through one file. But usually that's not the case. Usually you have lots of files, and it gets old really fast. Having to type out manual compile statements. So what people do is they have these utilities like AutoTools or CMake. I'm just going to call them the install system collectively. And there's different stages, but basically there's what's known as a configure stage, and it looks to make sure that everything is in order, make sure it has like libraries, and you have a compiler that works. And you run this configure program, and sometimes it takes like this input template make files, and that creates something called a make file. So based on the locations of different libraries, it'll build rules for compile statements. So you don't have to manually type them out. It's all here and described in the make file. And then you run make, and that produces the executable. And then sometimes there's a stage like make install, which takes the executable and then saves it to a predetermined install directory. And then I'm going to just add one more thing, which is if you're going to use modules as a source for your dependent software, most of our modules, they modify this environment variable package config path. And when you run that configure script, oftentimes it checks here. So here's an example of, I think this is a snippet from Python. So you'll see something like this. It does these tests, and you get a yes or a no. It tells you if it's available. Yeah, so if we're lucky, we just load the module. If we're unlucky, we may need to give the configure script some help and point it in the right direction. So here's running the configure script with this ncurses root option, so it can find ncurses. Oh yeah, and I mentioned earlier about those crazy long paths. This is like a convenience factor. You could add in like this ncurses _ root, or name of the software _ root. So you don't have to manually type out that whole long path. And if we're really unlucky, maybe we're just given a make file, we might have to manually make changes to the makefile. So here's, I don't remember what this is called, where this example comes from, but this is something that I had to do recently. Just add to the makefile. So we're going to do an example. The name of the software is unusual. It's called libcaca, and I'm not a big fan of the name, but it's actually a pretty good example, and it has a cool, actually does something cool. So let me switch my terminal. Okay, so here I am at my terminal. Oops. Okay, I'm just like clicking random stuff. Workshop. So I'm gonna, this is available on GitHub, so I'm just gonna do git clone. So if you're not familiar with GitHub, you do a git clone, and that's basically how you get the software. So ls, there's my directory libcaca. And oftentimes you have to run like this Bootstrap script. So let's run that real quick. And if you have a really fast eyes and good memory, you'd notice that this configure script is new. So I'm going to type ./configure and then help. And it tells you, since this is all like a generic build system, this auto tools, configure, make, install, a lot of the stuff is pretty generic and not helpful. But there is some stuff like enable ncurses. This is all pretty standard. Here's some environment variables. It says influential environment variables that we may have to modify. So, let me just point out one thing real quick. Installation directories. So we're going to use this prefix, which just tells you where you want to install the software. If you don't specify anything, it's going to put it here, and user local, which is a global installation. So if we didn't do this, we would get a message down the road where it gets mad at us. I'm going to configure and a prefix. Workshop. I'm going to put with demo, I guess. And hit enter. And now our screen is filling up with a bunch of stuff. But we can see it's doing checks, checking build system type, checking for its GCC, checking if GCC works, checking if G++ works. And here we're seeing it's checking for libraries, if they exist or not. So here it says it can't find something called ncurses. And no output drivers were selected. So you get this warning, and it doesn't really tell you anything's wrong. But if you go down the line and you actually build and install it, it doesn't work. So part of that is this warning. So what I want to do is I want to load the ncurses module. List. Load USC module. I'll just say ncurses. And I'll just rerun that configure script. And it fills up the screen again, finds a bunch of stuff. And here it is. And here's the portion that I'm interested in. Ncurses usability, ncurses present, ncurses.h not found. So this is what I was talking about earlier. We're not always so lucky. It doesn't work how it should work. For some reason, it can't find ncurses. And this is a pretty common thing that we're going to see because our modules are saved in what the configure script refers to as non-standard locations. So it's not in the places that it's looking in. So we have to help the configure script find it. So what we could do is we could use this utility pkg-config. Do something like C flags. So what is this thing that I just typed out? Well, in the message, it says can't find ncurses.h, ncurses w.h. So if I ls this directory, I can find ncurses.h, ncurses w. So this is the file that it's looking for. So this package config command utility is a really convenient way for you to get important file directories. So you don't have to go manually like adding stuff. So what I'm going to do is typically, configure script, it checks package config, but for some reason it's not doing that. So what I'm going to do is I'm going to run this configure script, but I'm going to add LD flags, which is pointing where libraries live, and, or is it CPP flags telling you where include directories are. I'm going to do CPP flags equal to C flags only I and curses. This is a nice convenient method. LD flags. Yes. So you also might be at this point wondering, like, why am I typing all of this stuff and what does it mean? Well, how would I know to type this is probably a better question. This is just like a trial and error. I've done this before and I've gone through this example. So it just turns out that you have to set these environment variables. And this turns out that this is a pretty common solution when you're building software and it can't find the dependencies. So I'll run that. Yes. And I'll do that configure. So now assume those checks again. And let's stop it. Where is it? Ncurses. So now we get something good. Ncurses availability, yes. Ncurses presence, yes. Yes, so this is all good news. It's finding Python, I guess that's all right. Now it's giving us this message. So now we have something called a make file, which is what I was talking about earlier. I can make try run. And it fills up your screen with basically what dry run does is it prints out what the make file is going to do. So this is kind of confusing to look at. But the thing I would like to draw your attention to is that there's going to be tons of lines like this. Oops, sorry. Where is it? The beginning, GCC. So these are all the compile commands that it's generating. So earlier I said, it's a pain to manually type compile statements. Well, this is all done through the make file. So I'm going to type make. We can see now it's telling you the result. It's compiling each code, each file, and it's giving you warnings. We'll just ignore those warnings. And while that's running, there's a question. What's the question? Where is the manual page for package config? And Luigi has kindly provided the relevant environment to help debug this. No manual entry. So let me just do that real quick. Just do this. Oh, I cannot type module. Okay, that would work. Yeah, so I guess I think Derek's here, but if I remember properly, I think just in general, manual pages aren't available because the expectation is that you'll be using what's in modules. So there's no manual pages there, but there's manual pages in the module, but there is no package config module. Therefore, no package config manual, but is the helpline. And actually, this is probably more useful than the manual. You can just see what options. There's libs only L, libs only capital L. So yeah, no manual page, unfortunately. Hopefully the help page is enough. Okay, so we did our make stage. Now I'm going to do make install. I'll just look really quickly at the make install stuff. So it's saying make install, and it's copying stuff around and giving you messages. Nothing to be done, entering directory. So let's go. Workshop. Okay, so here's my software. Maybe I'm not typing it right. I'll let Derek and Luigi duke it out. Okay, there we go. There's the manual page. We did it, everyone. Yeah, I guess this goes back to that philosophy I was saying earlier. We're expecting people to use the modules, so we're put more effort into manual stuff like manual pages there. Here we have our libcacas available. All our binaries. So I'm going to run just. So here it is. Here's our binary. It's running. Basically, it's an ASCII program, so it just shows you cool text and cool colors. So here it is, the fire. So it's working, and we can see in the terminal it says Kaka for N curses. So that's how we know it's, I don't know, it needed the N curses library to do whatever it's doing here. I'm gonna close that. This is a successful success. So if I wanted to create a module file, I would have to create a module file that adds this directory to the path. Let's go back to my PowerPoint. This is what I was saying earlier. We have to run this package config option. So we have a comment question. Basically, the question is why, so ncurses is a very common library. So why is it just not available everywhere? And so this is like another, I guess, the design philosophy, and it goes back to that compatibility issue. If we had something like ncurses, which is available everywhere, it's possible during this whole configure stage that it may pick up ncurses, we'll just say the global version of ncurses. It may pick that up instead of the module version, and that could cause compatibility issues, especially if you're doing something like you're building with the different compiler, because actually it turns out the system compiler is something like GCC 4, I don't know, 4 something. And we're setting the default one as GCC 8. So we want to minimize, let's say, contamination. We don't want most of your applications built with one compiler and then one snuck in. So yeah, I acknowledge it's kind of inconvenient that you're loading modules, but I think for reproducibility, this is my opinion, but I think it's worth the inconvenience. But if our users find that to be a problem, then yeah, definitely let us know, and we can change our design philosophy based on that feedback. Is there a second part? Yeah, so I guess if you wanted to, you could have a bunch of, I guess, a list of like common libraries like ncurses. You could have your own, we'll just say, developer module collection. So earlier I showed that module save, module restore. You could have your own version of that, or we could provide a version of that. And as you change compilers or something like that, using Lmod's, I'm not sure what it's called, just the feature that it has where it swaps modules around. I guess that's one option. If we get a lot of people asking for that, or you could do that yourself. Okay, so here's our example. Here's just like a list of like common issues that you may encounter. So like permission denied. It's usually when you're trying to do a global install. So you have to set a prefix. Undefined reference to library, something not found. You have to add to the library search path, header file not included. You have to add to the CPP flag or something like that. And so actually these are not, so I'd say these errors, they may be like more universal, but the solutions may not be very universal. But you will definitely encounter something like this on the error side. And then the way you resolve it is similar, but it depends on the build system. So in this example, this configure, make, install, this is how you would resolve it. If you're doing something like CMake, there's a similar way that you would go about resolving these same problems. It's basically a syntax. The syntax is different. Or if you're using some alternative build system that, because people don't like CMake and they don't like auto tools, it's the same idea, but different syntax. Okay. So next, we're actually getting near the end. So, a lot of people like to use Python, and we provide a list. We provide a set of Python packages. Let's go to the terminal. Let's go back to the terminal. Python 376. So I could do something like pip freeze. And this will give a list of every package that's available. So we have packages that we build when we install Python, and we update this as needed. In this case, I might have some stuff that may not be visible because I've installed my own personal Python packages. But yeah, so you can do pip freeze, you can see what's available. And if you wanted to install your own, you could do like I think of a good example. We'll just be TensorFlow. Already installed them. So yeah, it's already installed. But if I wanted to upgrade it, I could do upgrade, pip install TensorFlow upgrade. And it's going to do like a bunch of stuff, and it's going to run. This is taking longer than I expected, but eventually it should show me permission denied. And why is that? Because it's trying to install it in like this path right here, which is basically a global location. And root permissions is required. So what you would have to do is you'd have to add in this user option. I won't read it because it'll just take a long time and not really elucidate anything. But it'll install local. So this is like where all the Python packages get saved to. So yeah, it's possible. If you want to, you can install your own Python packages. If you want to use our Python, if you have your own version of Python that you like to use, you can maintain your own packages too. A lot of times, Python packages are wrappers for other libraries. So here's an example of H5Py. There's a library called HDF5, and it needs to know where your installation of that package is. So you can be, so this is specific to H5Py, but usually you have to set an environment variable pointing to where it is. Maybe you have to do a version, do a compiler. Then you can do your pip install, and it should be able to find it and work. But if not, you might have to just download the source code for the package and make some changes yourself. But I think in most cases, it's smart enough to, you can just do environment settings like this. Similarly with R is another popular programming language that people like to use. And I don't know the command off the top of my head, but yeah, we have R packages, a set of R packages installed. If you wanted to, you could install your own. R is smart enough to just automatically do a local install. But if you wanted to, you could specify a certain location. Similarly, some R packages are wrappers for other libraries. And in my experience, you have to look for this file, makevars, and that's where you add in those LB flags and CPP flags. But again, it depends on each package. And then finally, this is it's either like your first or your last resort. If the dependency chain is just too much, it's too tedious going around and looking for every package and installing it and making sure it works. Another option is something called Singularity. And this is a way for people to share what they call compute environments. And it's basically you, instead of sharing like the source code, you share this big Singularity file, and it has everything that it needs installed inside it. So it's a little bit like a virtual machine. For people who are familiar with Docker, it was built to be an alternative to Docker for an HPC cluster. So if you're installing something really complicated, maybe it's just easier to go with Singularity. And here's like a really cute example of a rainbow cow telling you your fortune. Let's click on the page real quick. Okay, so here's the Singularity page. And I'm just going to skip to this part right here. So this is a description of the Singularity image. So basically what happens is it installs like Ubuntu 16.04. After you get that base package, you can do all of your apt-get install commands. So this is pretty easy. If you can make use of what's called a package manager, you can just have someone else get your precompiled binaries for you. So it installs these apps, Fortune, Cowsay, and Lolcat. And then you can designate certain environment variables. And it creates something called a run script. So if you were to run the Singularity container, it would run this command, Fortune, take the output of Fortune into Cowsay, take the output of that into Lolcat, and then you get this rainbow cow thing. So typically with that, or sometimes people will build Singularity image files or definition files that describe like how to build the application. And so all you have to do is run the install, and then you have this image file. You can run your apps that way. Okay, so that's pretty much all of the material I have. As always, if you have any questions, you can send mail to carcsupport@usc.edu. We hold office hours every Tuesday through Zoom, and that's available. The link is available through our events page on our website. And you're here in a workshop, so yes, you know that we have workshops. We have a discourse page. If you have any questions about installing software, you can go on our discourse page and you can just ask anyone, or you can send in a ticket. And if you have a particularly tough package that you're trying to install, you can request a consultation with us. We'll be happy to help you. Are there any questions at this time? No questions? All right. Well then, thanks for your attention. Thanks for attending, and have a great weekend, everyone.